I'd like to look at some of the problems in Chapter 11. The first one is problem number 4. It says for inductors shown here, find the approximate inductance L in henries. You got 200 turns. The cross-sectional area is 1.5 10 to the minus 4 square meter. The relative permeability is 1,000, and the average length is 0.15 meters. Basically, just plug into the equation that L is equal to n squared mu sub r times mu sub 0 A divided by L. There's 200 turns, so it'll be 200 squared times mu sub r is 1,000. Mu sub 0, that's permeability of free space, which is 4 pi times 10 to the minus 7. Area has to be in meters squared, and the length has to be in meters, so it's all in the correct units. Plug into the equation, and if you calculate that, it gives you 50.26 millihenry. And number 7, it says if the flux leaking a coil of 50 turns changes at the rate of 120 milliweb per second, what is the induced voltage across the coil? Again, that's directly the Faraday's law that induced voltage is equal to n, the number of turns, times the rate of change of flux with respect to time. N is 50, and the flux is changing at a rate of 120 milliweb per second. So it'll be 50 times 120, milli times 10 to the minus 3. That has to be web per second to give you the voltage. If you calculate that, it gives you 6.0 volts. And number 12 says circuit in figure 79 composed of the standard values. First calculate, determine the time constant tau. So you have 4.7 millihenry, 2.2 kiloohms. That's determined the time constant, which is L divided by R. 4.7 milli divided by 2.2 K. That's 10 to the minus 3 divided by 10 to the plus 3. That gives you 10 to the 6. So 4.7 divided by 2.2. It gives you 2.14 milliseconds. Microseconds. Part B, it says write the mathematical expression for the current I of L after the switch is closed at time t is equal to 0. So everything is completely discharged at t is equal to 0, close the switch. And we had an equation for charging for the current to the inductor. Initially, the current is not going to change instantly. So the current would be equal to 0. At a steady state, it acts like a short circuit. So the voltage divided by the resistance, they give you the final value, which is this value right here, is 5.45 milliamps, e to the minus 1 e to the minus t over tau, which is 2.14 microseconds. Part C is determine the equation for the V sub L and V sub R after the switch is closed. When you close the switch, there's no current flowing, so the voltage across the resistor will be 0 initially. So all that voltage is going to appear across the inductor, so it'll be 12 volts. And it will exponentially go to 0 after 5 time constants, so it'll be E minus t divided by 2.14 microseconds. The voltage across R will be exactly identical to the current. You just multiply by 2.2 K. To give you the voltage. It'd be exactly the same waveform, except you have a 2.2 K multiplier. So if you multiply that, it's about 11 volts or so. Part D of the problem, determine I of L and V sub L for t is equal to 1 time constant, 3 times constant, and 5 time constants. So basically, you just plug into the equation. For 1 time constant, I sub L will be 5.45 milliamps. 1 e to the 1 time constant is just simply e to the minus 1. That gives you 3.45 milliamps. 3 time constant would be same value, 1 e to the minus 3. E to the minus 3, that gives you 5.18. And 5 is almost identical to 5 because it's already reached a steady state. It's about 5.41 milliamps. The same thing for the voltage. You just plug into the equation. 1 time constant is 4.42 volts. 3 time constants will be 12 e to the minus 3. That gives you 0.598. And the 5-time constant almost gets down to 0, 12 e to the minus 5, which is about 0.05% or so, is 0.08 volts. Part C of the problem says sketch the waveform for the current and the voltage. Current start out with 0, goes up to 5.45 milliamps at the 5-time constant. And if you multiply 5 by the time constant, which was 2.14 microseconds, about 10.7 microseconds, which is steady state, the voltage across the inductor is going to appear as maximum at t is equal to 0, and it will go down to 0 at 5-time constant. If you wanted to plot the voltage across the resistor, it's exactly identical as a current, but you have a scalar of 2.2K. And number 13, it says giving a supply of 18 volts, use the standard value to design a circuit. You have the response of figure 1180. So the current to the inductor is reaching 15 milliamps. That's steady state. So if you look at the equation for charging, it's E divided by R, 1 e to the minus t over tau. I sub L at 5-time constant is 15 milliamps. So 15 milliamps would be equal to, the voltage is 18 divided by R. The voltage is given, 1 e to the minus 5. And that's approximately equal to 18 divided by R, if you assume this will go to 0. So R then would be equal to 18 divided by 15 milliamps. That gives you 1.2 kilo ohms. 5-time constant is equal to 15 microseconds, so the time constant, 1-time constant is 3 microseconds. So plug it in, L is equal to then R times the time constant, or time constant is equal to L divided by R, so L would be R times the time constant. We calculate R 1.2K, time constant 3 microseconds. If you simplify that, gives you 3.6 millihenry. And those are standard values. And number 17, it says for the circuit shown, write the equation for the current I of L and the voltage following the closing of the switch. Note the magnitude direction of initial current. So you have some initial current of 6 milliamps to an inductor, and time t is equal to 0, you close the switch, and you want to calculate the voltage and the current to the inductor. First thing you want to do is convert the current source to the voltage source. So it'll be 4 milliamps times 2.2K. That gives you 8.8 volts. Now, if you go around the loop, again, when you do the conversion, this would be plus and minus like that. Plus is up and minus in the bottom, hooked up to the ground. So if you go on the loop, you go minus plus, minus plus. So 8 and 12 will be adding up. You got 20.8 volts total. And R total then would be R1 be connected in series with R2. And that's 2.2 plus 8.2 is give you 10.4 kilo ohms. So once you simplify the circuit, this is what you have. You got 20.8 volts source with a 10.4 kilo ohms. And you close the switch at time t is equal to 0. You have some initial current through an inductor of 6 milliamps. So I final, when the switch is closed, everything which is steady state, this acts like a short circuit. So you got 20.8 divided by 10.4. That gives you 2 milliamps. And the time constant would be L divided by R. 200 millihenry divided by 10.4. It gives you 19.23 microseconds. You have all the values. You put in the equation. I of L is equal to I of final plus I initial minus I final e to the minus t over tau. I final is 2 milliamps, 6 milliamps for initial, 2 milliamps for the final, e to the minus t divided by 19.23 microseconds. Simplify that. 6 minus 2 gives you 4. So that's the equation for the current. As soon as you close the switch at time t is equal to 0, again, this notation they use 0 plus, that means at the instance right after you close the switch. T 0 minus, that means before the switching. So right after the switching, this is what we have. You have as soon as you close the switch, the inductor dictates the current, so it's going to stay at 6 milliamps. So if you need to calculate initial voltage across the inductor, then you got plus or minus going around that loop, do Kirchhoff voltage law, 20.8 minus 10.4 kilo times 6 milliamps. And if you assume its polarity is like that, plus or minus, because that's the way they have it as plus or minus, then we're going to call that V sub I, initial voltage, has to be equal to 0. And so the initial voltage, which is the voltage across the inductor, T0 plus, that would be 20 minus, this is 62.4, that gives you minus 41.6 volts. So as soon as you close the switch, the voltage across the inductor will go down to 41.6 volts. And then it will go up to 0 after 5 time constants. So that's the equation for the voltage, that's the equation for the current, and it says sketch the waveform for both of them. It was 6 milliamps initially, so it's like that until t is equal to 0. Close the switch, it will drop down to 2 milliamps after 5 microseconds, 5 time constant, which is 96.15 microseconds. The voltage was 0, will drop down to minus 41.6 volts, and then we'll build up 5 time constant, will go to 0. And problem 19, it says for the network shown in figure 86, determine the mathematical expression for the current I of L and the voltage V sub L following the closing of the switch. So as soon as you close the switch, you need to calculate inductance. Inductance would be equal to 1 millihenry divided by 2. If I look at the terminal when you close the switch, we went to an example like this already in a lecture. You got 12 volts here. If I look at these 2 points to determine the Thevenin, if you're looking back this way, if you short circuit this, then this resistor would be short circuited, so R Thevenin is just simply equal to 2K. When you open the switch, then it would be different, but during the charging process, the voltage here would be 12 volts. That's your V Thevenin. Then R Thevenin is just simply equal to 2K. So when you calculate the time constant, when the switch is closed, this 10 kilo ohms is not going to come into the picture. It will not affect the time constant. So if you L divided by 2K, which is 1 minute here divided by 2K, it gives you 0.5 microseconds. I of L then would be equal to, that's the charging, would be E divided by R, 1 e to the minus t over tau, 12 divided by 2K, 6 milliamps, 1 e to the minus t divided by 0.5 microseconds. The voltage is going to start out at 12 volts. So as you close the switch, this current is 0, so all the voltage is going to appear across the 2 kilo ohms, the 12 volts, and then it will go down to 0 after steady state, so which is 12 e to the minus t divided by 0.5 microseconds. Part B, it says, repeat part A, if the switch is open at time t is equal to 1 microseconds. Well, this is 0.5 microsecond time constant, so after 2 time constant have not reached the steady state yet, but you open the switch, so you have some initial current here that we need to calculate. So t is equal to 1 microsecond, just plug into the equation here, it'd be 6 milliamps, 1 e to the minus, that's 2 time constant. So the current already dropped to 5.19 milliamps. The voltage at that point, the voltage crossed in the coil, is 12 e to the minus 2, is dropping down to 1.62 volts. Now when the switch is open, now you're going to discharge that energy of the inductor to the 2K and 2K and 10K, which is 12K. So you need to calculate an E time constant, which is L divided by R. Now it's 12K, that's tau prime. It gives you 83.3 nanoseconds. So when the switch is open, and this one is out of the circuit, you got 5.19 milliamps initially right after when the switch is open. That gives the initial value. But the voltage at 1 microsecond would be equal to minus 5.19 milliamps times 12K. That's how much voltage is going to appear, which gives you minus 62.28. because this is current is flowing that direction, so that's plus that minus, and which is equal to minus the voltage across the inductor at time t is equal to 1 microsecond. That's give you initial value. So V sub L then would be equal to minus 62.28 volts e to the minus t new time constant, and the current I of L after that is going to start out with 5.9. So here's a sketch of the waveform. You're starting out at 0, it goes up 1 microsecond and reaches 5.19 milliamp. It's not 100% a steady state. You open the switch, you're going to discharge it, so give up that energy. At that point, the voltage, which is started at 12, is at 1.62 volts. As soon as you open the switch, the voltage across the inductor could change instantly, and we calculated here at that moment. Instantly, the voltage is going to drop down to minus 62.28 volts. Get a huge voltage there. And after 5 time constant, 5 tau prime, which is much smaller than the previous time constant, so a lot faster, is going to give up that energy. So that's a waveform for both. And it says, yeah, sketch the waveform part A and B and the same set of axes. So this is part A and that's part B during the discharging cycle. Number 24 says, for the network shown, the switch is closed time t is equal to 0. Determine the V sub L as t is equal to 25 milliseconds. Very similar to the previous problem. The switch is closed time t is equal to 0. You need to calculate a time constant. This one is not in the picture. So when you close the switch, then you got 100 ohms and 20 is 120. So the tau then would be equal to L divided by R1 plus R3. That gives you 5 milliseconds. So the voltage V sub L would be E. Initially, there's no current initially. So all that voltage, the 36 volts, is going to appear across the inductor because there's no current flowing in here. So that's 36 e to the minus t divided by 5 milliseconds. So that's 36 at one time constant. 25 milliseconds. So 25 milliseconds divided by 5, that's 5 time constant. So the voltage across the inductor is almost very close to 0. That gives you 0.24 volts. Part B of the problem says find V sub L at t is equal to 1 milliseconds. At 1 millisecond, just plug into the equation, which would be 36 e to the 1 millisecond, so it would be e to the minus 0.2. Calculated gives you 29.47 volts. So it started with 36, and then we'll go down to 29.47 in 1 milliseconds. Calculate V sub R1 at t is equal to 1 time constant. VR1, you have the value for the current. You just multiply by the resistance R1, so it would be E divided by R1 plus R2, R1 plus R3, times, that's the equation for the current to the inductor, just multiply by the resistance R1. So that's 36 divided by 120 for R1 plus R3, 1 e to the minus the time constant, this is 1 microseconds, so the 1 divided by 5, times 100 for resistance R1, and that comes out to be 5.44 volts. Part D of the problem says find the time required for the current I of L to reach 100 milliamps. So this is the current for I of L, which is 300, 36 divided by 120. That gives you 300 milliamps, e to the minus t divided by 5 time constants. At 100 milliamps, just plug it into the equation. 100 milliamps has to be equal to 300 milliamps, 1 e to the minus t divided by 5 time constant, which 5 milliseconds for the time constant. Milliamp will cancel out. That gives you 1 multiplied divided by 100 give you 1. This is 3 minus 3 e to the minus t divided by 5 milliseconds. Take 3 to the other side of the equation, becomes minus 3, and multiply by negative 1, it gives you, and divided by 3. When you have an exponential function we discussed before, you must get the exponential function with a positive exponent on one side of the equation in order to get rid of the exponential function. So that gives you 2/3 e to the minus t, make it plus you invert this, so it'll be 3/2 be equal to e to the plus t divided by 5 millisecond. At this point, you're ready to take the natural log of both sides of the equation, get rid of the exponential function. So that's the natural log of 1.5 is equal to t divided by 5 milliseconds, or t is equal to 5 milliseconds times natural log of 1.5. If you calculate it, it gives you 2.03 milliseconds. So it takes about 2 milliseconds for the current to the inductor to reach 100 milliamps. And then part E of the problem says, what is the effect of a 470 ohm resistors? It's actually none. That's just to avoid the huge, if you open the switch, to avoid having a very extreme high voltage across the open circuit. So the 470 doesn't do any, it does not affect the circuit as far as the time response. Number 26 says determine the mathematical expression for the current I of L and V of L for the figure shown in 93. The steady state value of I of L is established before the switch is closed. So the circuit has been sitting like that for a long time before the switch is closed, so everything is open. So if I redraw the circuit, you got 4 kilo ohms hooked up to 20 volts to the ground, and you got 12K to the ground, and then 3K to the ground. So this is part to the left of the switch. On the right, you got R4 hooked up to the ground, and then you got an inductor on one side hooked up to the resistance R4, and that's hooked up to minus 8 volts. So we're going to make this plus to the ground, minus here, make that positive 8 volts. That's hooked up to the ground. So before the switching, everything is steady state. This acts like a short circuit. So you got plus minus 8 volts across R4. So that will give you initial current to the inductor at a steady state. That gives you 8 volts divided by 1.5K is 5.33 milliamps. And the voltage across the inductor is 0 before the switching. Now I'm going to calculate R Thevenin. If I short circuit this, look at these two terminals here, then R2, R1, and R3 all be connected in parallel. 4 in parallel with 12, it gives you 3. 3 in parallel with 3 gives you 1.5 kilo. So that's R Thevenin. V Thevenin would be the voltage across this parallel combination here. And so 20 volts is going to split up between 4K and R1 and R3 in parallel. R1 in parallel with R3 is 2.4K. So the V Thevenin at this point would be 20 volts times 2.4K divided by 2.4K plus 4K. If you calculate, that gives you 7.5 volts. So here's the circuit. You got some initial current, and the switch is closed. R Thevenin is equal to 1.5, and V Thevenin is equal to 7.5 volts. Now, R Thevenin now, prime, then would be 1.5K in parallel 1.5K. If you short circuit this, if I look at these two terminals here, that gives you 0.75 kilo ohms. And V Thevenin would just be simply 1/2 of the 7.5, which gives you 3.75 at each point, which is plus and minus. If you go around, that's minus plus, and this is plus minus. So those two will add up. Minus plus, minus plus gives you 8 plus 3.75. It gives you 11.75 volts. So to further simplify it, they got this part of the circuit. I'm going to replace it with the Thevenin and add it to 8 volts. So you get 11.75 volts connected to 0.75 kilo ohms, and then the inductor 3 millihenry. So tau then would be equal to L divided by R, 3 milliamps divided by 0.75K. That gives you 4 microseconds. So at a steady state, it's a short circuited, so the current would be equal to 11.75 volts divided by 0.75K. That gives you 15.67 milliamps. And we had initial current that we calculated initially was 5.33 milliamps. That was before the switching. You had 8 volts across 1.5K. Then it gives you 5.33 milliamps. So we had initial condition. We got to calculate a time constant. The final value is here. Just plug it into the equation. I of L will be equal to 15.67 milliamps for the I final. Initial is 5.33 minus 15.67. That gives you minus 10.34 e to the minus t divided by time constant is 4 microseconds. The voltage across the inductor just simply be equal to 11.75 volts e to the minus t divided by 4 microseconds. And see, part C of the problem. This is catch the waveform I of L and V sub L. I'll say part B of the problem says calculate yeah, that was part A. Part B, it says determine I of L and V of L after 2 time constant of the storage phase during the charging or storage. You have the equation, just plug it in. For the current 2 time constant, it would be 15.67 minus 10.34 e to the minus 2. That's 2 time constant, which is 8 microseconds. That gives you 14.27 milliamps. And for the voltage, would be 11.75 e to the minus 2, 1.5 volt, 1.59 volts. Part C of the problem. It says write the mathematical expression for the current I of L and the voltage if the switch is open at the instance defined by part B. So after 2 time constants, you're going to open the switch and then want to calculate the voltage and the current. So if the switch is open, so we already have initial current and initial voltage. I sub L at that moment, a 2 time constant is 14.27 milliamps in that direction. Now the switch is open, then you only have this part of the circuit, 1.5K, with some initial current and initial voltage and inductor, and 8 volts. So I final then would be equal to 8 volts divided by 1.5K, which gives you 5.33 milliamps. That's the initial, that's the final. Time constant is now the inductance 3 millihenry divided by 1.5K. Now it's 2 microseconds. So as soon as you close the switch, you open the switch, you got this initial current. It's going to go around the loop. So if you add up the voltages, should add up to 0 to calculate the initial voltage across the inductor, because that could change instantly. So if I go around the loop in that direction, you got 1.5K, that's negative, times 14.27 milliamps, plus minus, that's minus V sub L, minus plus, that's plus 8 volts, has to be equal to 0. So V sub L then would be equal to 8 minus 1.5 times 14.27. And if you calculate that, it comes out to be minus 13.4 volts. So as soon as you open the switch, the voltage across the inductance will go from 1.59 volts to minus 13.4 volts instantly, but not the current. So we have all the values plugged into the equation. I of final is 5.33. I of initial is 14.27 minus a final, which is 5.33 e to the minus t divided by 2 microseconds. Simplify that, it gives you 5.33 plus 8.94 e to the minus t divided by microseconds. And the voltage across the inductor would be minus 13 e to the minus t divided by microseconds. Part D of the problem, I ask you to plot the response for part A and C. So here's initially the current I of L start out with 0, will go up to 15.67. That's the steady state, but after 2 time constant, 8 microseconds, the switch is open, so it's already reached 14.27, and it's going to go down after 5 time constant. The 5 time constant now is 5 times 2. Before was 5 microseconds, now is 2 microseconds. So 5 times 2 is 10. That gives you 18. So after 18 microseconds, the current is already down to a steady state again, which is 5.33 milliamps. Same thing with the voltage. The voltage was 0. It went up to 11.75. After 5 time constant, it dropped to 1.59 that we calculated after 2 time constant, which was 8 microseconds. At that point, it dropped down to minus 13.4, and then we'll go back up again at 18 microseconds. We'll reach the steady state of 0. We'll stop here, and then we'll look at more problems in that chapter next time. Thank you.